Hello everyone, welcome back. We'll continue with the chapter 9, and chapter 9 we're going to focus a bit on attitude sensors. As we have seen before, attitude actuators, I think we have discussed, and we've been exposed to attitude actuators. Now we are going to actually look into attitude sensors. Well, since we have already discussed about attitude determination, attitude estimation, I think to get to know a bit on the principle of how attitude sensors work and what are our options, it's always good basically for the whole attitude control system. But again, we are not going to talk much about the design of the particular sensors, because each and every sensors are very unique, and the designs are very unique as well. But we are going to look at how these sensors are working and the principle of working of the sensors. And later we are going to see how we can actually benefit out of the sensors. Well, when you look at attitude determination, there are a few things that we need to take note. Basically, there are issues like accuracy, basically the overall measurement with respect to that exact physical values that we have. Then terms like arc minute is 1/60 degrees that you have seen, arc second 1/360 degrees that you have. And typical, I would say, terms that we need to use, like field of view. RMS is important. Basically, if you do navigation, root mean square. Basically, when you look at the navigation, especially when you do estimation, there's always a probability that we want to always cover. Technically speaking, we use sigma. Basically, when you do a curve, you do measurement, then you have a list of measurement, then you take most probable measurement. So we use statistics. Sometimes in navigation also we use basically Monte Carlo approach, basically to estimate the actual determination, or rather the actual value. Scale factors are normally used, especially when you have a physical system, hardwares. Technically, scale factors have been used basically to adjust the actual readings that you have. Please do understand, most of these devices readings are always with respect to the voltage, respect to current. So we need to calibrate that. Terrestrial, when you do calibration, then technically speaking, we should know how much of values that actually we generate. And last but not least, sensor axis is important. Again, back to square one. 3-axis is always been used, and it could be in if you install in a spacecraft, practically all those actually axes are going to be a body coordinate, just like a gyro. Or then based on that, actually, it's going to read how the spacecraft is going to react. In fact, how it's going to actually rotate in this particular body fixed coordinate. Well, these are the typical sensors that you can actually have. I guess we have also discussed this in previous lectures. When you look at all these options that we have, effect on the spacecraft, the most primitive way basically is a gravity gradient stabilized satellite. Cannot expect much of attitude, I would say accuracy, more than 5 degrees. Technically, it's basically passive way of stabilization. The first one means that you don't depend on any sensors. Even there's no point of having sensors, because you can't control it. So it's like a free fall, as you can see. So please have a look at the actual details. What are the implications with and without of the particular sensors? So as accuracy goes on, 1 to 5 degrees, as we can't actually go into passive. As I've thought, we may go into options like magnetometers, so magnetometers. So magnetometers you have, then obviously you need to actually have a sensor, basically to fit and to correct that attitude. So this could be one option that we have. So in this 1 to 5 degrees, we have sun sensors, could be one option that we have. Even magnetometers actually can be used accordingly. Accuracy goes even better, 0.1 degree to 1 degree. Then you have momentum bias stabilization. We have also discussed about that. You can go up to what, typically 0.1, 0.2. Yes, you need actually sensors. So we have, we can have magnetometers, we can have earth sensors, infrared sensors, etc. Now, the most, I think, typical or rather good quality satellites, we must have a good quality measurements. Assume that it's 0.1 degree or better. It could be even 0.001 degrees of altitude accuracy. Then we are looking at options like gyroscope. So that is mandatory. If you have those class of sensors, obviously you will have a good solid, I would say, actuators as well. That we have discussed in a previous lecture, reaction wheel, example, or bias momentum wheel. All those actually needs a very good sensor. Otherwise, it doesn't make sense basically to have a good actuator, but you have a very bad sensing. Right. Now, typical ones is basically very basic cosine detector sun sensor. So sometimes actually we say it's a cos sun sensor just to get the direction of that sun. It works obviously in a sun phase, not eclipse phase, because you need the sun. Just as we have learned in satellite technology, it is technically speaking, you will have a photovoltaic cells, and it's just going to actually be exposed to sun, and then there is a build-up of voltage, and therefore that you can actually say that you are facing the sun. So it's a very simple, I would say, sensor. Only thing is that as exposure what matters. So the intensity gets higher as we see. If you are normal to the particular sun vector, then you get a maximum exposure. Maximum exposure gives you a maximum voltage. So therefore, this can be actually detected. The location of sun, location of spacecraft with respect to the sun can be detected. Note that this can work only on sun phase. So it's not, but it's not going to be a very precise sensor. That is the reason sometimes we use, it's called a cos sun sensor, just to actually see where we are exactly, where actually sun and where is planet Earth. That meant. A bit more, I would say, having one, you can't do much. Probably having two, we can actually do slightly better. Yes, indeed. If you have two of those photocells, just like what you see here, then we should be actually we should be able to calculate the actual angle. That means where you are exactly heading, where basically how much is this particular angle, that should be able to be calculated. So it's a very simple calculation. I being the intensity. Now K value has to be calibrated. Once the K value is calibrated, the manufacturer will actually give you the alpha angle can be calculated. So that means, assume you are looking at let's say Z, and sun is at the back of you. Technically, you can actually have these two photocells looking at the sun. You run the algorithm. I can actually tell you exactly my negative Z, how much is that deviated with respect to the actual origin. So that gives you the alpha. That is easy to be found. So you must have two. Again, it works only on sun phase. Eclipse phase, you can't actually have this. Alright? Go on. Infrared Earth sensor. This is a very interesting sensor. The good thing about this sensor is that whether it's sun phase or eclipse phase, you can actually use the sensor. One of those very, I would say, commonly used sensor, even for LEO or even for geostationary orbit, you still actually can use this sensor. Principle of working, as I've said, it's just like a thermistor. Thermistor, which you can't see this heat, so to say. Infrared, you can actually also detect at night. So therefore, when you have this particular sensor, you should be actually able to exactly look at the horizon. How this works is simple. Imagine that actually you're looking at planet Earth from one spot. Technically speaking, 2D. So you will have a square. You will have a round or circular shape, and how this circular shape is going to actually move left and right. So that's how actually the fundamental how to do this. Let us see that one. This is how it is. You see, assume that this is the ideal one. This is a normal basically, and what we are going to measure is that how much of deviation that we have gone through with respect to the normal. I would say the ideal one. Now, in this case, please do understand we can only detect only two angles: the pitch and roll. Reason being, your Z is going to actually look at planet Earth. Basically, you're looking at planet Earth. When you look front, that's your flight direction. You can actually look at the horizon. And you look back, is also you can look at the horizon. So that's your roll direction. On the other hand, when you look at left, it's basically your pitch direction. But unfortunately, when you look down towards to Z, that is exactly on the planet Earth. That means it's all basically the terrain. You can see sea, etc. So that you can't detect. You can't actually have an horizon. So you can only see the land. So you all see, but you can't have the horizon. So which means that we can successfully have a detection of two axes, major axes, roll and pitch. In fact, when we can actually do this like detection or the attitude determination between for these two angles or the two axes, in fact we can allow the roll the yaw to basically to oscillate. So still we are fine. So we can live with it sometimes. Okay. A typical one, as I've said, just a look at the geometry. It is practically rearranging the geometry with respect to the ideal one to find the actual angle of a roll and yaw. Right? Go on. Now, slightly more expensive sensors, star sensors. Star sensors are, you don't, not any satellites actually is going to fly star sensors. Importantly, principal lens. Lens is actually going to look at your sky, and technically speaking, inside the sensor, you have already have a particular image, catalogs of images to technically to compare what exactly you see. Assume you are actually looking at the star, and we fix the body coordinate, we fix x, y, z practically, and with respect to x, y, z, technically speaking, you should be able to calculate the deviation. Okay, and the final angle, don't forget, the final angle basically, your phi angle is what actually is important. Okay, so with having those it's just a trigonometry function, having those angles basically, you should be able to calculate your x, y, and z. Technically speaking, all the three axes, the deviation of all the three axes of attitude, technically you should be able to calculate with the star sensors. Remember, star sensors are very, very precise. In fact, it's very, very expensive as well. So a very good quality of attitude determination if it's needed, star sensor could be one option. Otherwise, we don't embark on star sensors. Okay, very simple principle. All right, go on. Magnetometers. Now, magnetometers, as I've said, or rather as we have discussed, magnetic field disturbs us, and it is in terms of disturbance. But on the other hand, we have also magnetotalkers, where we use magnetic field basically to benefit the actual actuation. On top of it, the magnetic field allows us to actually do attitude estimation. Okay. Now, how this work again? Simple dipole model is what actually we use. Now, this I think you have seen this for the second time, I would say. I have repeated this. In fact, third time. In fact, I've shown this in the disturbances in planet. I mean, in an orbit. Then we went into the actuator, magnetic talkers, and again this has been re-invoked for the attitude determination. So it's a simple model, a simple dipole model. Attention, theta basically is shown here. In this case, for a simple calculation, what you can say, theta is basically an orbit angle with respect to ascending node. So for a start, basically you can assume that it's exactly at a zero. So when actually it's a zero, then you will have the orbital frequency only. So when you inject back in the orbital frequency this particular equation, this equation will look exactly like how you've been using for your estimation of disturbances, and of course your attitude actuator for torque, for mental talkers. So typically you can use for two estimation. It is a low orbit, low Earth orbit, or geo orbit. This can be actually always used. But again, when you're already flying in a geo orbit or geostationary orbit, well, I would say magnetometers might not be actually a good choice of a sensor, because it's going to give you a quite weak attitude results or attitude sensing capabilities. So again, we always use, in this case, we use a simple model, okay, for estimation. But again, go on. There's another model, basically split model. This, because as you know, that actually we are tilted. Planet Earth is tilted, so the whole magnetic field also is tilted. we can have this model, which is not very common, but advanced model, IGRF model, is what is commonly actually be used for estimation. So it's a very, I would say, rigorous in terms of estimation and calculation. If you want to do navigation, it has to be basically IGRF model for us to actually estimate the actual altitude. So I think I have also introduced this to you, two options that you have. Now, just you can remember, if you want to do altitude determinant estimation, IGRF model is what is desired. You can't get away with a simple model. But for altitude actuation, prediction, in fact, and the disturbance calculation, you can use a simple model because what matters is the maximum disturbance, or the worst case is what matters. In this case, every single moment we need to know how this actually magnetic model is evolving. Okay. All right. Magnetometers. Simple. For example, there are many types of magnetometers, and this case is actually a good common example would be a floodgate. Flux gate magnetometers. How this works is simple. If you have actually seen in physics, Hall sensors normally, what we say, Hall sensors, Hall, in fact, how it works basically, assume that you have electricity, you pump in electricity into this particular coil will be energized, basically there will be a voltage technically. So when you have a system which there's electricity is inside, there's a voltage build up, assume that there is a permanent magnet, you rotate around it. What you are exactly doing is that the voltage amplitude will be also basically distorted. So that distortion is exactly what you need to detect, or rather you want to detect. So you can go in a positive way or negative way, you will have the same amplitude. So once actually the field, you are submerged in the field, the actual voltage will actually vary. So when we can actually measure the actual variation of the voltage, we calibrate that carefully, we should be actually having the exact variation of the B field, or the magnetic field of planet Earth. So once we have the actual variation of the magnetic field, we have a complete model, or the IGRF model, as I mentioned just now. We can actually compare, and once you start comparing, then we know exactly what would be our attitude. It could be at all three axes we should be able to exercise, or rather estimate. But we can't actually start estimating simultaneously for all those three, sometimes because depending on the orbital motion. But as we have learned before, in any case, at least two per, I would say, cycle, it's highly accessible. Right? It's a very simple, I would say, sensor. In fact, it's a very small sensor. As you can see, it's just you can see it's as good as an IC nowadays. I think in our lab also we have in satellite lab we have I think done that in our lab exercises. It can be just an IC, and that is actually a magnetometers. All right. Again, don't expect a good or high accuracy of from magnetometers itself, not because of the sensor itself, but just because of the estimation that we want to do. So we need to do estimation. So the estimation is what going to give us or produce us the lesser accuracy in terms of attitude. Go on. So this is I explained already. So basically, external field intensity is what actually you measure. So you have once you energize the coils, you will end up actually having all those actually fields, and these fields are actually being generated because of the voltage and the variation. You bring in another magnetic field, there will be a variation of the voltage. When the variation of voltage can be measured, then you can indeed estimate the attitude. It's a very simple process. Very well, 1930s. The whole thing effect came in, and it's a very established, I would say, sensor. Go on. Gyro. So we have seen classes of sensors. Now come back to probably a good one. Gyros are very typical. In fact, in your aircraft, we use gyros. In spacecraft, when we have a very serious mission, yes, indeed, we use gyros as well. Just to understand the principle, this is a mechanical gyro. I think we still have it in ships. We still have these mechanical gyros. It works on a right-hand rule, if you will. rotation, basically there's a rotor basically rotating. Right hand rule, I use the right hand rule, it's rotating, so this is the rotation angle. Then you will have the torque, that means the input angle is here, let's say. Then my output will be actually this, along this line, which means that the input would be your input axis or input angle would be basically the actual external disturbances in spacecraft. So you can imagine gyro, okay, rotating. Assume this is basically Z axis, your axis, and there is an external disturbance which is actually disturbing torque. So this torque is what you measure. This is external. Okay, then the output is the deviation. It happens actually here in this axis. So as you can see, you embark the gyro, mechanical gyro, on Z axis to determine the exact disturbances along that to experience the disturbance torque along that particular axis, but the exact deviation that you have is basically on the perpendicular axis. So that's how the mechanical gyro works. But mechanical gyro, and then we can escalate the mechanical gyro through fiber optics gyro. Go on. Now in fiber optics gyro, sorry. Before we go into fiber optic gyro, mechanical gyros basically you have well, when we actually run the gyro, the output will be basically angular velocity, but there is also something called integrating gyro. And integrating gyro gives you the exact attitude. So you integrate that velocity, angular velocity, you should be having a readout would be basically the actual increment of the angle, that angle. Now, don't forget, just like a reaction wheel that we have discussed, this is a rotating, I would say, sensor. So you have a rotor which is rotating. So there is a chance of actual failure. So in space, basically, you do have, for example, reaction wheel. When we embark 3 reaction wheels, of course, 4th is mandatory in order for us to respect the redundancy policy. So therefore, gyro also has to be having this redundancy policy. You can see basically embark on all the principal axes, and then Q4 basically is going to dispute basically to as a redundant gyro in case of any of this failure in any other gyros that you have in all the other principal axes. Well, we can afford maybe one single failure, but we can't afford another 2 failures. So when you have 2 failures, then technically speaking, one axis will not be controllable. So you can afford only 1 failure in that sense. Yeah. Go on. All right. Fiber optics gyro, very very common. You could look at in space. I think we use a lot of fiber optics gyro. Fiber optics gyro, as you can see, what exactly it has a fiber optics cables basically, and you have fiber optic coils instead of any rotating elements. This is very reliable. In order to operate that, obviously you will have basically to inject the beam, the light beams. How this particular fiber optic gyro works is basically your beam. When you have a beam basically running through the fiber optic cables, you have a coil. Let's say this is actually amount of coil. Instead of having the rotation, you will have a coil, and assume that this coil is basically is along a particular axis. What exactly happens now when fiber optics has been lighted? So what happens when it flows? Is importantly basically it actually goes into the it respects the constant speed of light. Now what exactly happens when there is no let's say this is a stagnant motion, there's no motion, stagnant, so the speed of light is not going to be disturbed. So technically speaking, it's perfect. What you inject in, what comes out, the photo detector will actually detect exactly like what you inject in. But assume that there is a movement. Assume that there is a movement in this particular coil. The intensity of the light, that means the speed of light is basically being compromised. So what you detect would not be the same as what you inject in these fibers because of this particular movement. So that is very well calibrated. I should be knowing how much that I have rotated along this particular axis. So you can imagine. Now the good thing is that there is no rotating parts. There's no mechanical rotating part, so reliability is better compared to the mechanical gyro that you have. Go on. So this is quite famous. Okay, go on. Now we are looking at the sun sensors, right? Sun sensor, earth sensor. So how am I going to actually do this? Now these are the typical ones. Assume that this is my X direction, this is my Z direction. Sun sensors. Okay, what I'm going to do? I have here, for example, I have 3 sun sensors, 1, 2, okay, and 3 sun sensors. I'm facing planet Earth. Sun is at the back, but when I go into eclipse, these 2 sun sensors would be able to see the sun. Now when I'm facing the sun, obviously this is going to actually give me the maximum exposure, so this is going to work. But when I start orbiting, I go into the eclipse, then I want to come out, this will be actually very relevant to me. So during the sun phase, this is not going to work because this is going to actually face the sun, face the planet Earth. Only this is going to work. So if you want, when you just come out of the eclipse, you can actually already start facing the sun. You can see the sun actually. So these 2 is going to work. Now infrared. Infrared sensor is important. Infrared sensors. Now remember this, when you're always facing planet Earth, technically you should be able to use this easily because you are looking at planet Earth. Now assume that we have learned in orbital mechanics, before you start going into a particular orbit, in this case, let's say I am in a geostationary orbit, before you start actually going to the geostationary orbit, you need to actually pass through a transfer orbit. You can see, if you can remember, we do Hohmann transfer. In the Hohmann transfer, we have a transfer orbit. At the transfer orbit, when you are flying, your Z-axis, sorry, your X-axis, that is a flight direction. Technically speaking, your back is planet Earth. So this sensor will be actually used during the transfer. So that's the reason it's called a transfer orbit Earth sensors. And this is basically during the operation. Technically, you're already looking at the planet Earth. So there are many types of missions, or many types of. If you're flying very, very low, then you don't need this transfer orbit. Practically, one which actually faces the planet Earth is actually also good enough. And so it depends on this. This is just another example that you have. Now let's go further. Now, if you look at this, how this is this has been explained. I have Z, to planet Earth. I have stationary sensors, which is the basically infrared sensors. I have a pitch sun sensor, just like 2D just now. And here is basically my transfer orbit, infrared sensor and sun sensor as well. Now I think I didn't actually put in a transistor here. Gyro, assume that we are using a fiber optics gyro, it's also fine. And momentum wheel or even reaction wheel, it depends. Now actuators is not critical here. I haven't shown the actuators. In the previous lectures, I have shown the full blown of actuators, how the altitude actuators can be actually installed. So just imagine you superimpose the sensors and the actuators, then you will get a full complete satellite in terms of attitude control and determination. Gone. All right. Looking at sensor accuracies, well, ranges of accuracies. Now, important, basically, pay attention to the exact mass that actually you have, because it's going to be very, very critical. Now, if you look at initial references, for example, gyros, etc., it doesn't come in cheap because power budget is also quite high, and in terms of the weight is also, you got to actually take note of that. Sun sensors, please do understand sun sensors. There are actually, if it's give you a very, very fine accuracy, it is already, we are calling it not coarse, but actually a fine sun sensor. So fine sun sensor is actually can give you a very, very good attitude accuracy as well, but it doesn't come in cheap. There is a good amount of mass in there. Star sensor, as I've said, very, very good accuracy, extremely expensive. This would be probably, if you want your budget is a concern, then star sensor maybe it is the last option that you want to pick, because it can go into about 100,000 US dollars per system. Horizon sensors, quite cheap, reliable. Okay, magnetometers is the last in the list. Now, if you are doing any low cost, for example, a small satellite or a cube site, magnetometers might be the most, I would say, common that we use. Not much of accuracy that actually you can expect from these types of sensors. But again, what is the beauty is basically it's a very low power requirement, low cost mission. Is magnetometers is what that we always look for. Go on, have a look at it, and then all right. Thank you so much. Done.